For most of human history, our understanding of the universe depended on what visible light could show us. Stars, galaxies, nebulae glowing faintly across the sky. But visible light tells only part of the story. Much of the universe is hidden behind thick clouds of gas and dust. The earliest galaxies lie so far away that their light has been stretched by cosmic expansion, shifting it out of the visible range entirely. This is where James Webb Space Telescope becomes different. Webb was designed to observe the universe primarily in infrared light. Infrared wavelengths can pass through dust and reveal objects that visible light telescopes simply cannot detect. They also allow astronomers to see extremely distant objects whose light has traveled for billions of years. Webb's mirror, spanning 6.5 meters, collects far more light than any previous space telescope. Every photon it captures carries information from a time when the universe was young. Its location is equally critical. Positioned nearly 1.5 million kilometers from Earth at Lagrange Point 2, Webb remains extremely cold and stable. This allows it to detect faint infrared signals without interference from Earth's heat or atmosphere. James Webb was not built to replace Hubble. It was built to answer questions Hubble could never reach. When we observe deep space, we are also observing time. Light does not arrive instantly. A galaxy billions of light years away appears exactly as it was billions of years ago. For decades, scientists believed they understood how the early universe evolved after the Big Bang. James Webb challenged that belief almost immediately. Webb detected galaxies dating back to when the universe was only 300 to 500 million years old. According to existing cosmological models, these early galaxies should have been small, faint, and poorly organized. Instead, Webb observed galaxies that were surprisingly massive, bright, and star-rich, structurally mature. Some appeared comparable in size to modern galaxies like the Milky Way, despite existing when the universe was still in its infancy. This discovery created immediate tension in cosmology. These galaxies formed too quickly. They grew too large. They evolved too efficiently. And they should not exist in their observed form, at least not according to current theories. To understand why these discoveries matter, it helps to understand how galaxies are thought to form. Standard cosmology suggests a slow, hierarchical process. Dark matter collapses first, pulling gas inward. Stars ignite gradually. Galaxies grow through mergers over hundreds of millions or billions of years. James Webb disrupted this timeline. The galaxies it detected were already rich in stars and heavy elements. This suggests rapid star formation at rates far beyond what models predicted. Scientists now face difficult questions. Did stars form faster in the early universe? Does dark matter behave differently than assumed? Are feedback mechanisms weaker than expected? Or are our models fundamentally incomplete? None of these possibilities are simple adjustments. Each would require major revisions to how we understand cosmic evolution. James Webb did not provide answers. It exposed gaps. Some of the most important events in the universe occur hidden from view. Star formation happens deep within dense clouds of gas and dust. These regions block visible light, making them nearly invisible to traditional telescopes. James Webb changed that. By observing in infrared, Webb can peer directly into stellar nurseries. Regions once thought to be empty are now revealed as crowded environments filled with newborn stars. In nebulae like Carina, Webb detected protostars in early formation stages, jets of material ejected at extreme speeds, disks of dust around young stars, the raw material for planets. For the first time, scientists can observe star formation as it happens, rather than reconstructing it through simulations. This is not theory. This is direct observation. Where stars form, planets often follow. Around young stars, swirling disks of gas and dust slowly collapse into planets. Until now, these processes were mostly inferred from indirect evidence. James Webb has begun revealing them in detail. Infrared imaging allows Webb to detect warm dust within these disks, showing gaps where planets may already be forming. These observations offer rare insight into how planetary systems, including our own, may have developed. Understanding planet formation is critical because it determines planet size, orbital stability, atmospheric composition, potential habitability. James Webb is giving scientists the clearest look yet at the earliest stages of planetary systems. One of Webb's most revolutionary capabilities is its ability to analyze exoplanet atmospheres. When a planet passes in front of its star, a small portion of starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths, leaving detectable signatures. James Webb can read those signatures. So far, Webb has detected water vapor, carbon dioxide, methane, complex atmospheric chemistry. These detections occurred on planets hundreds of light years away. For the first time in history, humanity can measure the chemical composition of alien skies. This does not mean life has been discovered, but means we're no longer guessing blindly. We are collecting data. One of Webb's most revolutionary capabilities is its ability to analyze exoplanet atmospheres. When a planet passes in front of its star, a small portion of starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths, leaving detectable signatures. James Webb can read those signatures. So far, Webb has detected water vapor, carbon dioxide, methane, complex atmospheric chemistry. These detections occurred on planets hundreds of light years away. For the first time in history, humanity can measure the chemical composition of alien skies. This does not mean life has been discovered, but means we're no longer guessing blindly. We are collecting data. The search for life beyond Earth is one of the most sensitive areas of science. James Webb is not designed to detect life directly. Instead, it identifies biosignatures, chemical patterns that may indicate biological activity. However, nature can be deceptive. Non-biological processes can produce gases like methane or oxygen. Volcanic activity, stellar radiation, and atmospheric chemistry can create false signals. This is why scientists proceed cautiously. James Webb helps narrow the search by identifying worlds that deserve closer examination. It tells us where to look, not what to conclude. For the first time, the search for life has moved from speculation to systematic investigation. James Webb has also peered into the centers of distant galaxies, where massive black holes reside. What it found was unexpected. Some black holes in the early universe were already billions of times more massive than the Sun. According to current models, they should not have grown that large so quickly. This raises critical questions. Did black holes form before galaxies? Are there unknown growth mechanisms? Did early cosmic conditions favor rapid black hole formation? Black holes influence their host galaxies by regulating star formation and shaping galactic evolution. Webb's observations suggest black holes may have played a larger role in shaping the early universe than previously believed. The implications of Webb's discoveries are profound. If galaxies formed earlier, if stars ignited faster, if black holes grew more efficiently, then parts of our cosmological timeline may need revision. This does not mean the Big Bang is wrong, but it suggests that the period immediately following it may be more complex than current models describe. James Webb has reopened fundamental questions about how quickly structure emerged in the universe. And once those questions are reopened, nothing remains untouched. James Webb is only at the beginning of its mission. Its discoveries will guide future space telescopes, advanced ground observatories, target selection for life search missions. Every observation adds pressure to refine our theories and improve our understanding. James Webb's greatest contribution may not be what it finds, but what it forces scientists to rethink.